Welcome to our sixth and final lesson on stoichiometry, in which we look at the theoretical yield and the percent yield. So the theoretical yield is the mass of the product that's expected to be formed from the limiting reactant. In this case, this is just a problem, a stoichiometry problem like you've done many times before, in which you start with the limiting reactant. And the limiting reactant now is going to become the given. So this is like what we saw in the last lesson. So the limiting reactant becomes the given. And then the next thing we're going to do is ask you to find the mass of the product formed. So we actually did this before, didn't we? This is exactly what we did in the previous lesson when we found the mass of the product formed from the limiting reactant. And so this is a mass to mass or a mole to mole problem, depending on how we put it together. And this should be relatively easy to solve. So for example, here's a new reaction. I'm going to make you go through all the steps. We're going to go through all the steps. So we're given terbium-3 fluoride, that's an unusual compound, and calcium. And this is a single replacement reaction. I hope you recognize that. So we want to know what's the theoretical yield of the terbium that can be produced. So first thing we're going to do is determine the limiting reactant. We have to determine the moles of each reactant first. So take the TBF3 and multiply by 1 over the molar mass. Take the calcium, multiply by 1 over the molar mass. And find the mole equivalents. The mole equivalent of the TBF3 is 0.0635. The mole equivalent of the calcium is 0.0557. And because that 0.0557 is smaller, calcium is the limiting reactant. So far, so good. So now it's a simple mole to mass problem. The theoretical yield is almost always required in grams. I will tell you specifically grams, but if I don't want grams, if I want moles, I will specify that. So as we did before, we're going to start with the limiting reactant. There's our limiting reactant, calcium, to get to the theoretical yield of terbium. But again, we have moles, so we're going to go right into the mole to mole ratio. We want 2 moles of terbium over 3 moles of calcium from the balanced chemical equation. And now we're going to multiply by the molar mass of terbium. The moles of calcium cancel out. The moles of the terbium cancel out. They leave us with the mass of the terbium. And we have 18.4 grams of terbium as our theoretical yield. All right, so this is a theoretical yield, just like any mole to mass problem you've done before, any problem in which you just want to know how much reactant is how much product is going to be formed from a particular reactant. Now, percent yield is relatively easy. Percent yield is just the actual yield divided by the theoretical yield times 100, and this is this equation is found in chart B. So at some point, make sure you go and you find it in chart B. The percent yield actually indicates the efficiency of the reaction. The actual yield is either measured experimentally, and you'll be doing that in your lab, or you have already done this in your lab, or it could be given to you in the problem. Now you might ask yourself, why might we not collect all of the expected product in a reaction? Why is the percent yield less than 100%? Or actually it could be over 100% as well. And part of the answer to this is one of the reasons I ask you to evaluate potential systematic errors in the lab to find out what things might be able to be changed and fixed so that we might get our percent yields better. So one of the things is impure reactants. So if your reactants are less than 100% pure, you have less reactant than you thought, and so you won't be making as much of a reaction. Maybe you didn't collect all the products. Some of the products stuck to the beaker, or some of it was stuck to the filter, or somehow it did not all collect. This does not include, by the way, errors in accidentally spilling products. As far as the legitimate sources of errors, although that will affect your percent yield. Finally, side reactions. Side reactions are things, reactions that occur that sometimes we know about, they'll occur, but they aren't the reactions that we actually want, and so the products aren't what we're looking for, and so the percent yield of the product we're looking for is less than 100%. Why would you get a percent yield of greater than 100%? Well, that's going to indicate a contaminated product most likely. So the product can be contaminated with water if not fully dry, and with two products, one of them might contaminate the other. Keep in mind that when we're starting with our limiting reactant, there's no way to react more, to get more reaction formed than starting with the limiting reactant. So the only source of a percent yield that's greater than 100% is going to be some sort of contamination in your product. So the percent yield calculation is very simple. First, determine the theoretical yield as you did above, and then divide the the actual yield by the theoretical yield, multiply by 100 in the equation I gave you above. And so in the previous problem, when we found the theoretical yield to be 18.4 grams of terbium, if the actual yield is only 16.8 grams, what is the percent yield? So the percent yield, take the 16.8 grams of terbium, divide it by 18.4 grams of terbium. Now notice what cancels here, the grams of terbium and the grams of terbium cancel, multiply by 100, and we get 91.3%. So not always going to get 100%, and in all of the problems that I give you, not necessarily on the lab, but in the problems I give you, we're going to be looking for percent yields that are less than 100. So I've shown you how to calculate the theoretical yield and the percent yield. So now it's your turn. I will pause the video, and when you're finished doing your calculation, start it up again, and let's see how you did. Okay, so you're back. So let's see, we have iron 3 oxide, and carbon monoxide making magnetite, which is a mixture of Fe2 and Fe3 and carbon dioxide. First, we have to determine the limiting reactant. So the limiting reactant, the moles of the Fe2O3 and the moles of the CO. Let's find those mole equivalents, 0.144 for Fe2O3, 0.179 for CO, for carbon monoxide, and so the Fe2O3 is the limiting reactant because the 0.144 is less. So now the Fe2O3 controls all the rest of the calculations. Let's find out the theoretical yield. Starting with the Fe2O3, we have 0.431 moles of Fe2O3. Remember, we're starting with the original moles, not the mole equivalent. We're going to multiply by the ratio 2 moles of Fe3O4 over 3 moles of Fe2O3, and the Fe2O3 moles cancel out. Multiply by the molar mass of the Fe3O4, and now the moles of the Fe3O4 cancel out, and that gives us our theoretical yield. Now up above, I told you that the actual yield was 59.2 grams. So we're going to take that actual yield now and plug it into the percent yield equation along with the theoretical yield. 59.2 grams is our actual yield, that goes on top. The 66.6 grams of Fe3O4 goes on the bottom, multiply by 100, and that gives us a percent yield of 88.9%. So we're done with this lesson. We're done with the stoichiometry videos. Please go and read the section in the text, and I will see you in class.